Okay, so let's finish up the bias variance trade-off part. So in this part, we are going to give two examples. The first example is MAP for the Gaussian mean. So what does that mean is, suppose we are trying to estimate the mean of a Gaussian from a data set of x, y, I from 1 to n. So this is just purely purely statistical estimator. And we assume x, y is sampled from some Gaussian distributions of sigma square. Here we know the ground truth. Say we know the ground truth is equal to 1. But of course, when we do estimation, we don't know that. So what we can do is we can try the MLE estimation. We have done this before. So this will be mu hat equal to 1 over n summation I from 1 to n of x of I. So this is empirical mean. We know the bias is equal to 0. The variance of the mu hat is equal to sigma squared divided by n. So we did that. So total error, total test error, test MSE is equal to sigma squared divided by n. Second things we can do is we can do MAP. So then what we do is we have some Gaussian prior. So that means for the Gaussian prior says this has the form of normal distribution with the mu 0 and the sigma squared divided by and kappa 0. Okay, so that means my mu actually has this kind of prior distributions. I mean, if we do that, so you can and do this calculations, then my MAP estimation, I'm not going to go through the math. In fact, you're going to do very similar things in the homework. This will be n over n plus k0, sorry, kappa 0 of mu hat plus kappa 0 over n plus kappa 0 mu 0. So this is equal to 1 minus lambda of mu hat plus lambda of mu 0. And that this lambda is between 0 and 1s. Okay. So this things so actually controls how much you can trust MLE compared to the prior. So that means if it is and the lambda equal to 0, that means I fully trust MLE. If it is 1, I fully trust my prior. So you can actually think about this is like and the penalty terms. So in this cases, the bias actually is equal to lambda. So basically it's expected value of subtracted to mu star. This is 1 over 1 minus lambda of mu star plus lambda mu 0 minus mu star. This is equal to lambda of mu 0 minus mu star. Then the variances is basically MAP. This is equal to 1 minus lambda square of sigma square over the n. Okay, although like this MAP estimation is biased if we assume lambda is bigger than 0, and obviously we have lower variances in general. So then the total MSE, test MSE, and the total expected will be lambda lambda square of mu 0 minus mu star square plus 1 minus lambda square sigma square divided by n. That is possible. I mean, it's possible. This is less than sigma square over n. So that will, and you can do this estimation, which is and basically we can expand that. This, if we actually expand that, we can solve for lambda. And under what kind of situation? So basically, we can solve for that. So this is lambda square of mu 0 minus mu star square plus lambda square sigma square over n minus 2 sigma square over n lambda plus sigma square over n less than sigma square over n. So this tells you this is lambda is, we can factor out these terms, plus sigma square over n minus 2 sigma square n lambda less equal than 0. So that indicates my lambda has to be between bigger than 0, less than equal than 2 sigma square divided by n mu 0 mu star square plus sigma square. Okay, so we can choose the lambda in this region such that our biased estimator, which is MAP estimator, is actually performs better in terms of expected test MSEs compared to compared to the MLE. In fact, we can show right here, this is MAP. It reached the minimum at lambda equal to sigma square like that. So basically, if we choose this lambda and the lambda square, the expected test MSE. So minimum expected test MSE. So we can get even improved estimators compared to MLE. So what actually happened is because we are trying to using this MSE. MSE is mean square error. In fact, we can shrink error of the worst estimators. And even we just and like intentionally increased error. In fact, we will shrink the overall error because this square error will heavily punish these large errors, but can only moderate and punish the moderate errors because we take the square and for this error. So one way we can think about this is this square error is not the only error you should care about that. What will you and instead you can care about the sum of absolute errors instead of square. If you care that kind of situation, that you won't see such kind of like any phenomena. And this phenomena just tells you somehow MLE estimators is not the best choices. It turns out it will be better to adding some shrinkage. Adding some and specifically make your an estimators and like slightly smaller will make your estimator better. But and we can explain things clearly mathematically, but this result is very counterintuitive. So that's why this idea is quite crazy. But this just the math is quite clear, and you get some like very simple estimators. In fact, if you just make this estimator slightly smaller, in fact you can and perform better in terms of test and MSE. Okay, in fact, we're using this kind of tricks and techniques and a lot in practice. So this is some idea called a shrinkage. So basically, if you have some estimator, you are going to add some and usually in these cases will just be simply an identity here. Sorry, that's not this one. And just being identity here. So you basically just adding some values and make your and the whole estimation slightly smaller. So this is just a statistical estimator. And we can do this for the model as well. We can do this for the ridge regression again. So we can do the MAP estimations for the ridge regressions. So what does that mean? I want to remind you my solution for the ridge is basically we're trying to find argument of xw minus y plus lambda of the two norms. So this is equal and has analytical solution, which is x transpose of x plus lambda of identity of D inverse x transpose of y. This model right here, and the model that we have is very simple. Is y equal to xw plus epsilon. So here we are going to make some simple assumption that assume x transpose of x is actually an identity matrix. So this is not very reasonable. And we're trying to illustrate this whole idea here. You can think about this xij is roughly a Gaussian distributions with standard Gaussians that on average if we take this and X transpose X, this whole thing, if like the dimension is large enough, it will be close to be a Gaussian, an identity matrix times the n's. If we, if we allow these things, we can like analytic plugin right here. This is becomes n of I identity plus this inverse of X transpose of Y, which is XW plus epsilon right here. Yes. So this is becomes, and it's basically 1 over n plus lambda X transpose of X. Again, it's this an identity of W here plus 1 over n plus lambda X transpose of epsilon. So the bias here is an expected value of f hat subtract to f. This is equal to this is equal to expected value of x of w hat of ridge subtract to x times w. So this is nothing but so like everything here that will be gone because epsilon has expectation of 0 here. So this will be x times I would say n of n plus lambda of x of w here subtract x times w. So this will be minus lambda over n plus lambda of xw here. Okay. Yeah, I think I missed the lambda minus sign here in the note. The variance which is this term. This is the variance of x of w hat ridge then this is becomes x variances of w hat ridge x transpose. This is, and we can plug in the variances of w hat ridge. And because everything here, this will be deterministic, the variance is all coming from this part. So, and basically this will becomes the following. It's 1 over lambda x transpose. The variance of epsilon is sigma square x and 1 over m plus lambda, the x transpose. So this is and the little x here. And this is the big matrix X. We know this is identity times n. This becomes X transpose of x times of n over n plus lambda sigma square. So this is equal to n sigma square over n plus lambda norm of x right here. So that means the bias variance in total which is the expected value of the test MSE is the bias square plus variance plus the noise variance. So this is equal to, the first term is lambda square plus n plus lambda which is xw square plus n sigma square n plus lambda square norm of x square plus sigma square. So what does that tells you right here? This whole thing, based on what kind of x you are and inputting, and relate that, and you can find optimal lambda such that the and bias square plus variances is minimized. And you can be sure this lambda right here will never and the reached optimal cannot be like and when lambda is 0. So that means adding a little bit ridge penalty or L2 penalty is give some and it will be helpful to reduce the test MSE here. But of course, in general, this whole thing will, depends on the x and depends on w right here. Practice, the way that we do is we're using the cross validation to find out the optimal lambda. And you can see actually this lambda, it depends on the data, depends on and the problems. In this cases, it will be difficult to find out optimal lambda analytically, but the point that you see is, and such like optimal lambda does exist in theory. Okay. And also another way, and this is, and basically we give two simple examples. But the issue is, if you are given a very complicated models, how can we choose the best models, right? So, and here we are just, you can see, even for the rich regressions, this whole and the derivation is very complicated. We need to even make some unrealistic assumptions. For example, my x transpose x has to be n times identity, which is unrealistic. But in practice, how can we sure we can, and how do we choose the best models in theory? And of course, in practice, we can use cross validations, but in theory, how does this being done? So this is the question, is how to choose best models. So this question is being addressed by using statistical learning theory. So this is being very and very important theories in machine learning. So basically the whole idea is we can rewrite everything that is expected test and test MSE. It should less equal than the training MSE plus some additional function here. It's n, it's h and eta. And we're going to talk about an h and eta and momentarily. So n is always the size of training set. This h here is the measure of the model complexities. So you can think about it's sort of close like degree of freedoms. And the eta here is the probability that this bound fails. Okay. So that means like we need this eta probability to allow really unlucky training and the testing data set to be happen. But usually it's really a small numbers. Could be like 0.001. So the ideal way is we need to choose this model complexity that actually minimize the bound of the test error. So in practice, you will see, in general, you will see this, like test MSE should be a little bit bigger than the training MSE in general. But if you see something like your and your training MSE is super small, then your test MSE, and your training MSE should be smaller than and the test MSE. But if you see your test MSE is significantly larger than the training MSE, that means you are encountering the problem of overfittings. So the key here is to measure the model complexity here. So this is being and measured call, and this is measured by like it's called like Advanced Trigonometric dimensions, and usually we just call it VC dimensions. Okay, so and you can think about if the model complexity is higher, that means we have like higher and higher power. I mean, it's more power and powerful complex functions, but it might overfit. If and this BC dimension is small, that means it has less power. It won't overfit, but it will be limited to what we can like represent. So, and how we quantify that? I mean, this is quite. Give you some idea and how we actually quantify that is we think about it. We pick endpoints and assign them of plus sign and a minus sign randomly. Okay, so this is something a very interesting. Well, for example, we can so a model class can shatter a set of this endpoint for every possible labeling of all the points. Then there exists a model that can class that with the zero training errors. So what does that mean? And for example, suppose our model is the hyperplane. So we only have a 3 point. Then we have a 3 point of which, for example, we have a 2 plus 1 minus. You can draw a line that and to separate them perfectly. If you have all the plus, you can also draw a line to separate them and perfectly. And for these 3 points and on a plane, you can always and shadow them, and you can always find a hyperplane to separate and like plus sign and a minus sign. So that indicates a 2D hyperplanes can shatter 3 points. But 2D hyperplane cannot deal with 4 points. For example, we have plus sign and a minus sign right here. There's no way that you can draw a line to perfectly separate these in a situation here. So this is a typical codata set called XOR. Right, so that means the VC dimension of 2D plane, 2D hyperplane, is actually 3. So that means it can shatter 3 points, but it can not shatter the and 4 points. So this is purely like you can see, and in general, I mean D dimension. So this will be D plus 1. But sometimes it's perfectly possible this and it could have like infinite many dimensions with only 2 parameters. For example, a sine wave, like hx is equal to a times the sine of bx. It has infinite many of VC dimension and with only like 2 parameters, because you can and shatter almost any random set on 1D points. Say you have this, you can make this period so small and carefully that you can shatter any random set. Like this, you can always like shatter them, and everything in like below will be plus, everything above will be circles. And of course, there'll be some very special cases that it won't work, but these cases will not happen in reality. So that's why a simple sine curve with only with only 2 parameters, A and B's, in fact, could have infinite numbers of VC dimensions. All right. So, and we have a talk about this right here, but we haven't talked about what is this F right here. Right. So I'm going to and tell you and what is that and precisely. So this actually requires some assumption here. So the assumption is if you have some model class, for example, it has some like an hypothesis space. It could be polynomial in a space. And all these D, is drawn in IID manners. And also, this is the training. All the testing data is drawn on the same, the same data set. And from same distributions in IID manners. Then my expected test MSE is less equal than training plus h of logarithm of 2n over h plus 1 minus logarithm of eta divided by 4 divided by n. So with the probability of 1 minus eta. So you can choose eta to be very small, like 0.01. We have such kind of, and we can such kind of bound. But the issue is this bound is quite loose. It's just give you some insight. In practice, it's not really helpful. This just give you some idea and what kind of things that you are working with. And also in general, this H is nearly impossible to estimate if you are given a model class. Okay, so, but this can give you some insight on your models. For example, if your hypothesis space is very big and relative to the size of training and the data n, for example, very high degrees of polynomials on neural network, and the neural network has a very high degree of freedoms. That means it's very likely to overfit. And if your H, like hypothesis and space, is sufficiently constrained in size, that means we consider this as and has a low VC dimensions, and also the size of training data n is really large. That means if we only have very low training error, it's likely to be the evidence of the low testing error as well. So, and let me write down this and carefully. That's if H is very large, that means we are working with very flexible models, very complicated models, likely to be overfittings. If H space is constrained, in size, and your n, which is training data, is large, then low training error likely can implies the low testing error. There's no guarantee here. Everything just has probability, is likely, and with high probabilities per se. Okay, so this just gives you some idea what you should be looking at in general. Okay, so let me just demonstrate with some code here. So this is some code that you can run. So here we just consider a degree 5 of polynomial model, which is one of the simplest model that you can think about. That I come with the 40 and the data here. And so this is my ground truth, which is quite complicated. So the ground truth is, as I said, is 5 and a degree 5 polynomial. And we adding some Gaussian noise. So then we generate an additional test data set. We plot them out and with the ground truth. So you can see this is so the red is testing data set, the blue is the training data set, and this curve right here is the ground truth. So And I want to emphasize this is training data set and testing data set, they don't overlap, right? So it doesn't, and we need to make sure the testing data set is, it's never being used in the training, and this test error is independent of the training error. The test examples is coming from the same distributions and with the new examples. And we want to understand how this test error behaves theoretically. So this is the point. We consider the expected test error, which is the true error right here. So the key things is test error is unbiased estimator of the true error. And the true error is obviously is not unobservable, but we care the most is the true error. So we use the test error as kind of the surrogate or an approximation of the true error. So in order to compute that, we simulate this process is why we get more and more samples. Then we train these new predictors again with the new samples. So it is important to understand this predictor right here is actually a random functions. So that's why we can and ask what is the expectation and so on, and the variance and so on. So the randomness is coming from this training data. So that means we and repeatedly do and generating and these datas and again with the 40s of trainings and the 100 testings to actually approximate the test errors. So we're going to run this 100 times right here, and you can see this is and we repeat it to and work with degree 3 polynomial regressions, degree 5 and polynomial and regression, and degree 15 and polynomial and regressions. Then we plot them out. So this actually gives you 3 regions. So this is the underfitting, this is overfitting, and this is the perfect fitting. So this is the right amount and the ground truth that we should be working with. So you can see right here, if for the degree of 3, it has a very high biases because, and you can see this is my average fit, which is my red lines. It's very different from the ground truth, and each fit, and which is the green line, and varies with average fit of the red lines, and with relatively small and variances. But overall error, you can see is very high right here, just because my bias is very high. But my variances is not very high because you can see it only fluctuates very moderately. For this degree 5, it's almost perfect. It has a very low bias. And you can see this red curve and the black curve almost match very well. And also, the variance is also very small, just because we happen to know this is perfectly fit to degree 5. It's just very small variances, and overall, and we sum them, and overall testing errors will be small as well. On the other hand, on the degree of 15, it gives you relatively small bias as well, because and you can see if we take expectation, this is quite close to the ground truth of black, but each individual fit varies a lot, really a lot about this an average. So that indicates we have very high variances right here. As a result, total error with a bias square plus the variance of each individual fit will be very high. So that's why the reason of overfitting is not because of the bias, it's actually the high variances from our fittings. It's because of those things. Those things is really bad, and create so those high variances and contribute to the high test MSE errors. All right, so this is a quick demo to give you a good idea on underfitting, overfitting, and the right sweet spot. So this will be high bias, low variances. This will be low bias and low variances. This will be high and low bias and high variances. Okay, so these are the three regions that we'll be interested in. Okay, so that's all for this part.